In this video, we're going to talk about algebraic treatments of limits. So we'll start with limit laws. These apply to all limits of all the functions that actually have their limit existing at a particular point. I'm not going to prove them or justify them. Please take a look at the book to see a more careful treatment of why these actually work. But the limit laws essentially say that if I have two functions that are well behaved around point A, in the sense that their limits at point A exist, so again, remember that limits care about what happens near a point, not at the point. So near the point A, both functions are nicely behaved. Then you can do all kinds of things to the limits. So if you compute the limit of a sum, f plus g, you can actually break them apart and compute the limit of the first function, limit of the second function separately, and then add the limits together. Okay? Same with the difference, same with the times. Again, instead of computing the product of the functions first, you can compute the limits separately and then take the product. Same with the quotient, except for, of course, in the quotient, the bottom cannot be 0. And then there's this very convenient, there are these two really convenient laws that can actually be derived from the above ones that say, look, if you have a function f of x multiplied by some constant, and this constant does not depend on x. Limit is computed when x approaches something. So if inside you have a constant that doesn't depend on x, you can take this constant outside of the limit. Okay? And if you have a limit of a function to some power, then again, you can compute the limit separately and then raise the entire limit to the power, as opposed to just raising the function to the power first. Okay? And we'll see how these apply shortly. These are limit laws. Let's talk about how to actually compute limits from an algebraic expression. So the first rule of limits, I call it just plug it in. The book calls it direct substitution rule. So direct substitution rule says if the function is nice, then you just plug it in and the value you get is the value of the function. So what does it mean to be nice? It means not have any unexpected behaviors at the point. So remember from last video about when does limit not exist. It's things like holes, like jumps, like asymptotes, like oscillations. So if we're not talking about those cases, we will call the function nice. So nice means no holes, no jumps, let's say. No finite jumps, non-infinite jumps, so no asymptotes. So most of the functions that we will work with are generally nice except for at certain points. So for example, polynomials are always nice functions, right? They never have holes or asymptotes. Rational functions are mostly nice except for at the asymptote. So rational functions, except for when the bottom, the denominator, is equal to 0. Things like trigonometric functions, so for example, sine and cosine are nice smooth curves. You can always calculate any limit along them. Except for, of course, like tangent already starts to have asymptotes. Things like this, like exponential functions, they have mostly, they're mostly well-behaved logarithms and so on. So the more functions we see, the more functions we will analyze with respect to holes, jumps, and asymptotes. So if you can plug it in and there are no issues, then you're done. You got lucky. This is a nice function. This is just the value of the limit that it is. The second rule of limits is just plug it in anyway, because plugging it in will help you diagnose the problem. Helps diagnose the issue. And once you know what the issue or problem is, you can actually solve it, right? If you have no idea why this function is not nice, then there's no way to actually approach it. Once you plug it in and you see what is creating an issue, we can target that issue. Once you diagnose the problem, there are a couple of ways to actually target the issues. You can try to simplify an expression. So it's things like factor things out or multiply by a conjugate are the two most common techniques. Or we can try to justify or by conjugate, we can try to justify or reason out why a limit is a certain value. Okay, and we'll see examples of both shortly. So let's take a look at the first one, where we have a rational function and we're asked to compute the limit at 3. So again, first rule of limits, plug it in. Let me write this down. Plug it in. So we're going to take the value that we're given, x approaches 3. So I know that once again, when the limit is computed at x approaching 3, it's not actually at 3, it's just around 3. But let me plug in 3, and if there is no problem at 3, then the limit is as the function value. So if I plug in 3, x equals 3 into all of these x's here, so 3, 3, 3, what am I going to get? 3 squared is 9, 9 plus 3 is 12, minus 12 is 0, so the top is 0, and then the bottom is 3 minus 3, so also is 0. Well, that's an issue. Now, I'm going to put this in square brackets because this isn't really quite the number that I'm actually computing, right? I'm not really supposed to be plugging in 3. Limit is what happens around 3. So this isn't really 0, it's a number close to 0, and I have no idea how close it is. In particular, I have no idea how close it is with respect to this other 0. I don't know what the relationship of these two zeros is. Is the top number much bigger than the bottom number or the other way around? Okay? But this allows me to diagnose the problem here. This 0 on the bottom is really an issue. I cannot divide by 0. That's not allowed. So this x minus 3 on the bottom is creating the problem. So what can I do to get rid of it? Well, let's take a look at this limit to begin with. I can see that the top, I can probably factor out. So let's try that. So we're going to try to factor. And what are we going to get? If the limit stays there, because we haven't computed yet, the top factoring out gives us x minus 3, x plus 4, and the bottom stays x minus 3. Well, this is fantastic news, because now I can cancel out the x minus 3's, and remember that it was exactly the x minus 3 that was creating the 0 on the bottom that did not allow me to compute the limit. Okay, so once that gets canceled, I can rewrite this as limit of x plus 4. I've canceled out my problem. Now I have myself a new limit, which means that I can try to plug it in again. My original problem should not exist anymore, so maybe I have no issues whatsoever. Okay, so we're going to plug it in again. And what do we get? Well, if I plug in x equals to 3 into this x here, I get 3 plus 4, which is 7. Okay, no issues. If you get a number, that's your answer. Okay, so it is important to note here that this function isn't actually the same as x plus 4, because this original function did not exist at 3. It has a hole at 3, right? And so this function doesn't quite describe this function perfectly at 3, but it describes it well everywhere else. So I can compute the limit at 3, even though my original function does not exist at 3. Okay? Okay, let's take a look at the second one. And again, we have a limit. The very first thing you're going to do is plug it in just to see what happens. And here, what are we going to get? If we plug in 0, x goes to 0. So if I plug in 0 here and 0 here, root of 9 is 3. 3 minus 3 is 0. Divided by 0. So once again, I get 0 over 0. Once again, I'm going to put it in square brackets, signifying that I'm not actually computing 0 divided by 0. I'm computing something close to 0 divided by something close to 0. But because I cannot compute that directly, now I have an issue. And again, it's actually the 0 on the bottom that's an issue. I can divide 0 by something, but I can never divide by 0. Okay? So this 0 on the bottom comes from this x being on the bottom. So I would like to somehow simplify or massage this expression, hopefully, in order to get rid of the x factor on the bottom. Okay, so let me take a look at this guy here. What can I do? I cannot do any kind of factoring on the top. It's not a polynomial. I mean, here it was nice and quadratic. This one is not a polynomial function, so I can't really factor. It would be really nice to get rid of the square root, though, wouldn't it? And this is where you're going to have to be extremely careful. I like to say that simplifying is like putting makeup on. It can change the way it looks, but it should not change its value. Okay? So you cannot just decide to plop a square on top of it, because now the expression is not the same as the old expression, and simplifying should not change the value. Not to mention that actually plopping square on top will not get rid of the square root. So the one common technique to get rid of the square root is to multiply by conjugate. So to multiply by the exact same expression, but instead of the minus separating the two pieces, you're going to have a plus. Because we're going to multiply by the conjugate, in order to keep the value, we also have to divide by the conjugate, okay? So your next expression is actually going to be your original function written out fully. So minus 3 all over x multiplied and divided, again, so as to not change the actual expression, by the function's conjugate. So the exact same thing, but with the plus in the middle, okay? Now, please pause the video and actually try to factor things out on the top, okay? So on the top here, maybe I'll put in the brackets, I'm going to actually FOIL the whole thing out. So I have to multiply everything throughout, and I'm going to get one long expression, but things are going to really simplify quite well. So pause here and actually do the algebraic manipulations yourself. As I've mentioned before, math is not a spectator sport, so watching me do a bunch of algebraic manipulations is not actually going to make you any better at it. So please pause and try to open up the brackets, try to simplify. Okay, so now that I trust you've actually tried this for yourself, I'm going to write down the expression that you should have gotten. Once you do a bunch of these, you will notice a pattern, or maybe if you practice this quite a bit in grade 12, you already know that the difference of squares will give you the square of the first term minus the square of the second one. Here, though, foiling it out, I see that the first thing I get is root of x plus 9 times root of x plus 9, which is x plus 9. And then I'm going to get the root times 3 and the root times minus 3, so they will cancel each other out. And the last term is 3 times negative 3, which is minus 9. But my bottom is going to be this entire expression, okay? Maybe let me move it here. Nope, won't fit. Okay. All right, so what happens here now? These 9s can go away, plus 1 and 9 minus 9. And so what I have left is limit as x goes to 0, x over x, and my remaining conjugate on the bottom. And now this is also really great too, because now that I have x by itself as a factor on top, I can cancel it out with the x on the bottom, okay? And remember, why this is really great news is because this 0 coming from this x on the bottom was exactly the reason that we couldn't just plug in and compute the limit in the first place. Now I've canceled this x out, so hopefully that issue went away and I can just plug it in and get a number. Okay, so what happens here? Well, x on top went away and there's 1 that was remaining, so now I can plug it in. What am I going to get? Actually, let me just rewrite this. Limit as x goes to 0 of 1. Note that I've canceled out x. I didn't cancel out all of the top. There's still going to be 1 remaining. So x plus 9 plus 3. And if I plug it in now, all I'm going to get is 1 over root 9 plus 3, so 1 over 6. That's fantastic news. I just got a number, which means that there were no more issues. I've managed to simplify, massage this issue away. So now I can just compute limit as a number. Now let's take a look at some limits where we just have to plug things in and be able to justify it. So there's nothing really to simplify, and therefore we're going to have to apply some other kinds of justifications to them. Let's take a look at this first one. So as x goes to 0, I'm interested in the fraction 1 over x. What happens here if I plug it in? I'm going to get 1 over 0. And again, that's not something that I can compute, so I'm going to put it in square brackets. But what does that really mean? I'm dividing 1 by a really, really small number. Okay? So let's pretend you have yourself a pizza, and you're dividing it into tiny, tiny little pieces. How many pieces are you going to get? Lots. The smaller the pieces, the more of them you're going to get, right? And because it's the limit as x goes to 0, you're actually looking at tiny, teeny, tiny pieces. So you're going to get a ton of them. The mathematical way to describe a ton of them will be to say infinity. And the symbol for that is sort of a sideways 8. Okay? On the flip side, what happens if you do the exact opposite? So what if x goes to infinity and you're wanting to compute 1 over x? So I have 1 over infinity essentially. And again, I'm going to put this into square brackets because infinity is not quite a number. It is a concept of a number that is larger than anything that you can think of. So what happens here is I'm dividing 1 So again, one pizza, let's say, into a ton of pieces. How big is each piece going to be? If I'm dividing into many pieces, the more pieces I divide into, the smaller each piece is going to be. So this is like the exact opposite of the question before, where now I'm going to get a 0. This is also helpful to consider in terms of a graph. So for example, for 1 over x, the graph of a function looks like this. Whoops. These guys are asymptotes, and they're symmetric. Let's pretend this is nice and pretty and smooth, right? And so as x approaches 0, from the left or from the right here, notice that I didn't actually specify, and so my infinity doesn't have a plus or minus sign. So if I'm approaching, let's say, from the right, as I go toward the graph, my graph, the closer I get to 0, the higher my graph climbs. So the closer I get to infinity on that side. On the other hand, if I approach infinity, so that means that I keep going further and further along the x-axis. So I keep going further and further along here. The closer and closer to the x-axis my number is going to become. If I divide by 1,000 and then 10,000, a million, 10 million, the smaller my outcome is going to be. Okay, let's take a look at these other two. So again, first rule of limits, plug it in. So what happens if I plug it in? I get 2 to the 0 over 7. What is 2 to the 0? Any number to power 0 is 1. So it's 1 over 7, and we're done. There's no issues here. There's no problem having 0 in the power. The last example here, again, first rule of limits, plug it in. So plug it in, I get 0 over 2 to the 7th. Dividing 0 by anything except for 0 will give you 0. If you have no pizza, doesn't matter how many friends you get, you're still not going to be able to eat it, right? So 0 divided by something is 0. You can divide 0, but you cannot divide by 0. So be careful about that. Let's take a look now at our very first application here, Lorentz formula. Hendrik Lorentz was a Dutch physicist he was actually a Nobel Prize laureate. He won a Nobel Prize in 1902. He's one of the most influential physicists of our time. He's the one that laid foundations for special theory of relativity, as well as some of the quantum theory that physicists are working on today. So this is the formula that is known as Lorentz formula, and it describes the length of an object at certain velocity. Okay, so the formula has a bunch of constants and no real numbers, so let's label all the known quantities, or all the quantities that are actually in the formula. So this v is the object's velocity or speed. This c is the speed of light, so everything is compared to the speed of light. This L0 is the object's initial length. So let's say I take an object, my car, and it starts traveling faster and faster. What the question is asking is, and what the formula is actually giving us, is the length of the car as perceived by an observer as it moves at a certain speed. Now, the question isn't actually asking to compute the length at a certain speed. It's asking to compute the limit of this length as the velocity approaches the speed of light. So let's first of all write out in words what is it that we're trying to compute. There's always two parts to a limit. There is what it is that you're trying to compute, and where are you computing it at. So what is it we're trying to compute? We're trying to compute L, which is the length of an object. Okay, we're trying to compute it in the limit, which means that this is the length the object approaches, right? That's what we're trying to compute, the length that the object actually approaches as, and then where are we computing it at? We're computing it as velocity approaches the speed of light, and it's important to note here that it's approaching the speed of light from the left. So my object, my car, let's say, accelerates toward the speed of light, not decelerates towards it, okay? So length of an object, we're computing the length the object approaches as its speed approaches the speed of light. I don't know if you guys can hear, but the crows outside of my window are going crazy. So if you can hear that on the video, I'm sorry. There's nothing I can do about them. Okay, the The first rule of limits, we're trying to plug it in. But now the first thing we're going to try to plug in is to actually replace this L with a formula for it that is given by the Lorentz formula. So limit as v goes c from the left of L, which is given by L naught, 1 minus v squared over c squared. Excellent. Now, in plugging it in, here I'm going to have to be a little bit more careful for two reasons. First of all, I'm asked to plug in something that is c from the left. So not c, but a quantity that I know is really, really close to c, but smaller than c. So I can plug in c, but keep in mind that whatever it is that I'm plugging is just a little bit smaller. And the other problem is the square root. This is where normally some issues can arise. Either division by 0 or computing square roots of negative numbers. Those two operations are not allowed. So if all of a sudden I have a square root where whatever is underneath is negative, that's going to be a problem. So let me plug in c minus and keep that in mind as we're doing some of these computations. Plug it in. Okay, so what am I going to have? I'm going to have L naught. I'm going to put it in square brackets if there is an issue. Otherwise, I'm just going to keep it as is. So I am plugging in v goes to c minus. So I'm plugging in c instead of v. C is an actual number. Speed of light is a known constant, right? So I'm plugging that in instead of the velocity. Whoops. So I'm going to have 1 minus c squared over c squared. Okay, pause here and make sure you actually understand that I just replaced this v with the c. Now, the one small nuance here is, again, I'm actually replacing, maybe I should put it in a slightly different color, this c guy here. This is the one that I replaced, right? This c, I know, is a value that's just a little bit smaller than c. So when we're analyzing, we're going to have to take that logic through with us, okay? So let's see. Here I have c squared over c squared. A number divided by itself is always 1, but here I know that the number on the top is just a little bit smaller than c, right? So this quantity actually approaches, this guy approaches 1, but from the left. It's just a little bit smaller than 1, which is in fact very good news, because now I'm doing 1 minus something slightly smaller than 1, like 0.99999 or whatever, right? Which means that the outcome of this operation is positive, which means that I will be able to actually take a square root of it. I'm not taking a square root of a negative number here, so we're all good. Okay, now with that in mind, I can actually compute what happens next, right? So I'm going to have L naught square root of 1 minus 1, because that's what my quantity approaches. 1 minus 1 is 0, a positive 0 here, right, on the positive side. So it's going to be L naught times 0, which is 0. Okay, so my ultimate answer here is that as an object approaches the speed of light, its velocity approaches 0. That makes sense. Try to justify that to yourself.